नमस्तुभ्यं वरदे कामरूपिणी विद्यारम्भं करिष्यामि सिद्धिर्भवतु मे सदा पद्मपत्रविशालाक्षी पद्मकेसरवर्णिनी नित्यं पद्मालयां देवी सा मां पातु सरस्वती भगवती निःशेषजाड्यापहा।
Good evening everyone, a warm welcome to all. So today is the third session of our ongoing monthly webinar physics series. I welcome all the delegates to this session. Last 2 months we had a great talk by Dr. Pudiyavan, who took some basic classes on how the MR images are formed, and one of the difficult topic in MR physics is the K space and the parallel imaging. And to make that difficult topic make it easier, we have none other than Professor Sanjaya Viswamitra. He basically did this, he is graduated from Jawaharlal Institute, Jipmer, Pondicherry, and he also is a USA board certified nuclear medicine physician, one of the great combination. Currently he is heading the Department of Radiology at Sri Sathya Sai Institute of Higher Medical Science, Bangalore. He is also a faculty at University of Arkansas at Little Rock, USA. So currently he is in USA and is giving a talk from there. He is our ex-president of Indian Association of Cardiac Imaging, and without any further delay, I welcome Dr. Sanjaya to start the session. And yes, it is one of the difficult topic to understand. Yeah, only those who have some basic idea can follow these things, but yes, this is a very important area to understand the overall MRI image formation, and as well as to understand some of the artifacts. Sometimes you will be wondering why some of the artifacts are happening and how to rectify it, and if you have a better working knowledge of this case space, it will be very useful. And especially now with the availability of parallel imaging, and different techniques are using based on the case space undersampling, all those things we know that. So today Dr. Sanjaya going to explain how these things works and what are all the basic physics you should be aware of. Yes, over to you, Dr. Sanjaya, please.
Rajesh, thank you so much. Thank you again to the IACI for inviting me. I hope all of you can hear me clearly and also see my screen.
Yes, please go ahead.
Okay, great. So my talk today is going to be on K-space and parallel imaging, and my objectives for the talk are basically to help you understand the concept of K-space, discuss imaging techniques in relationship to the K-space, and also touch upon parallel imaging. Acknowledgements is due to my mentor, Dr. Donald Mitchell from Thomas Jefferson University Hospital. He has set me on the path to understanding MRI about 20 years back, and this is a textbook which I would recommend that you may find useful in your journey to understanding MRI principles as well. So the main question is, why do we need to learn about K-space? What is it that is so important about K-space that every single MRI physics lecture discusses it in some degree or the other? And the reason we need to understand it is because we need to think about how the magnet looks at images, how the magnet looks at a patient. So the magnet acquires images in K-space, and therefore our understanding, as Rajesh already mentioned, will help us improve the speed of acquisition and also to problem solve artifacts. So all of you are familiar with what a magnet looks like. This is just a cutaway of the magnet. You have the liquid helium in the middle. You have the superconducting coil around it, and you have gradient coils, which are also radio frequency coils, which basically excite the set of protons within the patient, allowing you to basically get some signals, some frequencies. Now, these are in the frequency space of signals. This is an example of how a magnet will look when it's being made. So you can see that these are the superconducting coils that you have here. And these surface coils that you see here with these curved appearances are the coils in the X gradient, Y gradient, and Z gradient. And in the last two sessions of the physics lectures, you have already heard how these gradients are responsible for giving you echoes. Now the question is, what happens to those echoes? Those echoes basically are frequencies, and the magnet sees them in this space on the left, and we call this image on the left as K-space. What we then do is we do a set of complex Fourier transformations, some mathematical transformations, wherein we take the information of these frequencies on the left and achieve an image on the right, such as this. Okay? So Fourier transformation is what converts the K-space into an MRI image. Why is this concept, why is it called K-space? It's called K-space because the frequencies are described with the letter K. I can see here that the K-space is basically the original description of spatial frequencies. And hence, it is we continue to refer to the spatial frequency domain. We listen to echoes. Echoes are basically nothing but frequencies. And we put that into a space, and therefore this is called K-space. It can also be called as momentum space. This is another name for it. So let me describe first what a Fourier transform is. And I want you to listen to these sounds, and I hope these sounds are going to be loud enough so that you can all hear at your stations. What I'm showing you here on the image on the left is a very simple single frequency. And it's basically going to sound something like this. Okay. Now I'm going to add some more complexity to the frequency, and you can hear the frequency as well. Sorry. And even more complexity. Notice that you have some ups and you have a lot of different types of frequencies which are embedded within this frequency map, within this basically waveform. And yet you're still able to basically you're able to hear complex sounds. You're able to take complex sounds such as this and convert them into simple, straightforward, discrete frequencies, which is what Fourier transform does. Okay. Essentially, what we do on MRI, and you've seen these images before, is we have this radio frequency pulse. This is a slice encoding gradient has already been given, and we get these echoes. These echoes are achieved at different phase gradients, right? So GP is the phase encoding gradient, and we see these echoes are achieved at different phase encoding gradients. Each of these gradients are then in the frequency readout gradient. They are plotted along the frequency gradient. So let me again just describe this in a simple manner. What you see here is a description of K-space. K-space has a y-axis, which is the phase encoding axis. It has an x-axis, which is the readout axis. Notice that the x and y-axis are not identical to our Cartesian plane, our understanding of standard planes, because these are frequencies which are depicted here. Notice also that for every single TR that we get, we have one new line of phase encoding that we get. Okay, so in the first 1 through 8 points that we see here, which are mapped along the frequency encoding gradient, then we repeat the repetition time, we get another phase encoding gradient, another phase encoding step, and so on and so forth till we fill up all of these 8 different steps. So the first thing that we can understand from this concept here is that it takes a certain amount of time for us to get the entire K-space. We need to get the full K-space so that we can get an image. And the time that we take to get K-space is dependent upon the repetition time, which is the amount of time between each of these phase encodes, multiplied by the number of phase encoding steps that we are using to fill up K-space. I hope that is clear by now. The second important thing that we see here is the center of K-space that you see here is filled by the stronger echoes. The echoes which have lower phase encoding gradients fill up the strong, which give you stronger echoes, fill up the center of K-space. So two very important points from this pulse sequence diagram. The time of acquisition is nothing but the repetition time into the number of phase encoding steps. The echo time and the frequency encoding steps are not included in this equation because they are automatically included within this repetition time itself. I think that should be clear by now. Okay. So let us now understand how that translates into unique features of K-space. Okay. So the center, remember, has got the higher echoes, the stronger echoes. It represents contrast, C for contrast. The periphery or the edges has got the lower echoes, the weaker echoes, and they represent sharpness or edge detection. So the low frequencies, but stronger strength echoes are in the contrast. The higher frequencies, but the lower strength echoes are in the periphery, which give you resolution. Okay, so now these are all words, and I'm sure that all of you are already feeling a little sleepy by now because these are some mathematical principles. Let me show this to you in the form of images. On the left-hand side, you see the K-space, and on the right-hand side of the image, you see the MRI of the brain, which is the exact representation of this K-space that you see here. So this is the frequency domain. This is the image domain that we see here. So remember, I told you the center is contrast. So I've discarded the periphery of the K-space. Notice that I'm still able to see the contrast in the brain. I discard a little bit more. Now I have only the center of K-space, which I'm using to generate this image. Notice that I'm getting these Gibbs truncation artifacts because I'm just not getting enough information to give me a good detection of the edges and the boundaries, but I'm still able to very nicely appreciate the contrast of the brain on this image by showing you the center of K-space. Center implies contrast. What if I discard the center? If I discard the center, I only have the edge detection, so you can see the edges. But because it is not a complete K-space and because there's a limitation of the number of frequencies that I'm showing you here, you're still getting this Gibbs truncation artifact, but you are now seeing only the edges. You've completely removed the contrast in this particular image. I give you a little bit more of the periphery, still removing the central K-space. I'm able to see the edges to an even better extent. I hope this little experiment shows you that the center corresponds to contrast, the periphery corresponds to edges, but we need both for you to get a good quality image. This is a very important concept, which I will repeat when I talk about parallel imaging. On the face of it, if you look at this image of K-space, it looks like a standard K-space, right? It's taken, it looks the same size of all the K-spaces that I have shown you earlier. However, here on this particular image, the dots that you see here, which represent all the frequencies, are actually spread apart a little bit more. So when you undersample K-space, when you spread apart K-space a little bit, you essentially make the field of view smaller. Okay? You induce the field of view to be smaller. Okay? We will come back to that when we talk about parallel imaging. The other important point that I mentioned to you is that the frequency space just looks like multiple dots which have a very somewhat of a symmetry on that particular image. It's important for you to appreciate that any point in K-space, every point has got some degree of information about the entire image. So I'm going to play you a song, and I want you to think of what images you see in your brain when you hear this particular snippet of the song. And I am told that historically this song, though it was in a movie, historically this song was made because there was an MRI person who wanted to hear the song of T1 singing to T2. Okay. So perhaps this song is familiar to some of you, and I'm playing the song. I want you to close your eyes and see what images you hear. Okay, so let me play the song.
ख्वाबों का कारवां और फिर चल दिए तुम कहाँ हम कहाँ।
Sorry. So I'm sure all of you got some images in your brain when you saw that. Essentially, what you heard was just one song, right? So you heard one very complex frequency in your brain, but your mind was immediately seeing the pictures of Lata Mangeshkar, Sonu Nigam and Lata Mangeshkar. Maybe you felt that you saw tabla, you could hear the violin, see the violin, you could even see the guitar. Your brain essentially did the Fourier transform for you. So it took this, they took the frequency space that you heard and converted it into the images that you were able to see. So that's essentially all that it is. K-space is nothing but this same type of conversion. We do it mathematically, your brain is doing it constantly. Okay. Here is another example of how to point out exactly that every point in K-space does contain some information across the image. So on this particular K-space, you notice that there is one bright spike that I'm showing you here, just this one extra spike, right? Everything else seems to be completely uniform in this particular image. What do you think this particular image is going to look like when I convert this image space into, when I convert this frequency space into an image space? This is what you get. You get the spike artifacts that you see here, and you can see that the spike artifacts are distributed as bands across the entire image. Right? So a single bad point in K-space has got some information across the entire image. I hope that has now become very clear to you. The other thing that I showed you here when in this little exercise that I did when I was taking these frequencies and converting it in from a complex spectrum is that you notice that there was some degree of conjugate symmetry around this midpoint 0. Do you all appreciate the fact that there is symmetry between the negatives and the positive? There's symmetry between the upper part and the lower part of K-space. It turns out that this symmetry is diagonally located. So that means the left upper quadrant symmetry is now reflected in the right lower quadrant. So that's the area of symmetry. And this is also the symmetry on the opposite side. How does this help us understand acquisition techniques? So potentially we could now just acquire only a little bit above 50% of K-space. And because we know that there is symmetry, we can fill up this area of K-space by using the data that we already have on the opposite side, right? And we can then get an image. Now notice that when I told you about what controls the time of the sequence, TR multiplied by the phase encoding steps, right? I have now reduced the number of phase encoding steps in my acquisition, which automatically means that I have make the image much faster, right? So this is one way of speeding up the image, and we typically end up using these in sequences such as the single shot fast spin echo sequence or the half Fourier acquisition sequence that we often use. When do we use it? A nice example is when the patient can't hold still. So here you have an example of a fetus where you basically you are using the single shot technique to get a very fast sequence, maybe just about 1 second for you to acquire this image. And you can see that it is extremely sharp and well delineated without any motion that you see on this particular image. Now, one question that you might have for me is that, okay, so I'm not repeating the repetition time in some of these very fast sequences. Therefore, I'm getting multiple phase encoding steps. Each of them have a variable different TE. The initial phase encodes might have a smaller TE. The end of the study, the sequences may have a longer TE. So what is the echo time for this particular sequence? And the answer goes to the understanding that the center of K-space represents contrast. So whatever echo time is used to fill up the center of K-space is the echo time for this particular image. Okay. Now, do we have any problems by doing faster images like this with partial sequences? The answer is yes. Every time you try to get faster and faster sequences and you reduce the amount of filling of K-space, you will get artifacts such as this. You can see the blur artifact in this partial encoded image compared to the much more sharper image on the left where the full K-space was acquired. Okay, so you get a little bit more blurring on the image on the left. So there is some degree of blurring that you see. What about 3D acquisition? We all have 3D sequences. How does K-space translate into 3D acquisitions? So the 3D acquisition is nothing but a volumetric acquisition of K-space. We call the depth as a partition gradient. The frequency and the phase encoding gradient is the same in the same usual direction. And the partition gradient is acquired by using a second set of phase encoding steps. So you have the slice encoding step, and then you have the first set of phase encoding steps. And then you use the second set of phase encoding steps together with this to get the partition as well. So the advantage of that is that you are now able to get 3D images such as this, which are very nice. You're able to get good spatial resolution. You're able to get much smaller spatial resolution. In fact, notice this is a 4 millimeter slice thickness compared to a 7 millimeter slice thickness, because you're getting volumetric data. But because of the addition of the second phase encoding gradient and the additional time that you require for that particular process, this particular exam has gone from a 5-second breath hold to a 25-second breath hold on this particular image. And there was iPad fractals which are used on this particular exam. So are there any problems in using 3D gradient other than the fact that the time might be a little bit longer? So remember, you have a second set of phase encoding gradients. So when you have a second set of phase encoding gradients, unfortunately, any artifacts which propagate along the phase encode, such as motion artifacts, are worse on a 3D sequence compared to a 2D sequence. So this is an example of a patient who had a 3D sequence on the right and a 2D sequence on the left. You can see that here, 2D sequence here, 3D sequence, right? It was done at exactly the same time on the same date, just minutes apart from each other. But because this has a second phase encoding gradient, you see much more motion artifact on the image on the left as compared to the image on the right. So a bit of a recap here in terms of where we are going with K-space and what you need to do to further understand K-space. So I was talking to Yoda, because some of you may have heard of Baby Yoda. The original Yoda I could not meet, so I had a chance to meet Baby Yoda in Hollywood when I was visiting US. And he was telling me this joke. So he said that there were 3 friends who met after 20 years. And while they were talking, one of them asked, what would you do if your doctor said you had only 6 months to live? Immediately, the first friend said, I would give up everything and go to the Himalayas and meditate, because that's what I need to do. Second friend said, I would sell everything that I have, and I would go on a world cruise. I would enjoy myself. So Baby Yoda said, do you really know what the actual answer is, what the true answer is? The true answer is what the third friend said, which is that he would get another doctor's opinion. K-space is in somewhat ways similar. I'm going to give my lecture, I hope, is going to really help you understand K-space and formulate the way of understanding K-space, but you really need to get other opinions and you need to understand it from multiple texts so that you are best able to use the nuances of K-space. So let us now move on to the unique features of K-space, which might help us as we move forward with our using K-space as well. First thing I mentioned was that there can be multiple ways of filling K-space, right? One can even share echoes across anatomy when the anatomy is constant. So this is an example of 3 different ways of filling K-space that you see here. The first is called the centric method, where the center is filled first, and then you fill up the outer rows. You can do the sequential method, where you start from one end and you just go all the way to the other end. Or you can do the keyhole filling method, wherein you fill up the outer rows first, and then you keep on repeating the central K-space and share the information that you have from the outer rows on all the subsequent images that you have, as long as the anatomy doesn't change. Now imagine what happens, right? So we said already that K-space, the speed of an acquisition, simply put on MRI, is TR, the repetition time, multiplied by the number of phase encoding steps. So here, if you're sharing the outer areas of the phase encoding steps, then you're never repeating this. All you're acquiring is only the central number of lines of K-space, which may be about 30, 40, maybe 50. Hence, the repeated images are going to be much faster than the initial first image, where you took all the lines of K-space and then you're sharing different data across. So now you have the ability to get images such as this, this is an example of a time-resolved imaging contrast kinetics, where in a patient who's got Raynaud's syndrome, you're trying to visualize the blood flow, the gadolinium enhancement in different parts of the hand, and you're able to see it at about 1.2 second, 3 second intervals. So dynamic imaging becomes much more feasible when you use the centric keyhole type of K-space filling and you're sharing the outer data, as long as I said, the image anatomy, the edges do not change of that particular image. There is another type of filling, which is called the radial cine filling, which is sometimes used in cardiac imaging as well. And this is how you use radial filling as well. Each of them have certain advantages, right? So radial case space is said to have a higher spatial advantage, higher temporal resolution, no phase wrap because it's in a radial projection. So you really don't have any narrowing of that particular region of case space. But it does have more pronunciation, more pronounced streak artifact at the edges of the field of view. And it requires a more complex mathematics for you to get Fourier transform rather than the simple mathematics. So it takes more time and it's more intensive in terms of how you do it. These are just examples taken from Gary McNeil, who is a Siemens expert, who shared these images with me showing radial segmented cine images on the right and this Cartesian segmented cine images on the left. These are older images, and I'm sure that we get much better images now, but this nevertheless shows you that radial case space is one option that we have. I'm sure all of you, if you go back on your system and look at your system, you will be able to see an option where you can choose radial filling as well. As I mentioned to you, the problem with radial filling and some of these non-Cartesian imaging is that they are time consuming because they use non-uniform Fourier transforms. It's a bit more complex method of reconstructions. So what do we do in cardiac imaging? Typically, we either use prospective or retrospective gating. We need one set of case space for each phase of the exam that we see in the cine sequence. So phase 1 is given in green, phase 5, let's say, is given in purple, and phase 10 of the cine loop is given in orange. So you just look at we're just showing you some portions of this area. And typically you need multiple heartbeats. You acquire maybe about 5 lines of case space, 10 lines of case space, and you put them in each heartbeat, and then you repeat it in multiple heartbeats till you fill up the fully sampled case space, and then you get one image each. So that's typically how we go from a retrospective gating to image analysis, image acquisition. Again, we can try to do this in a smarter way and try to make this even faster. And this speed is called segmented acquisition of case space. So in the previous examination, I gave you an exam where you could basically take 5 lines of case space, fill it up for each heartbeat, and then overall, over a period of say 10 heartbeats, you have 50 lines of case space. Over a period of 20 heartbeats, you have 100 lines of case space, which let us just say for this example, you need to get one image. So how long did it take me to get one cine phase? It took me 20 heartbeats. Patient has a heartbeat of 1 second, one beat per second. It's taken me 20 seconds. 20 seconds is a long period of time for a person to be holding his breath. So maybe 5 doesn't work out that well. Maybe I need to go to 10. If I use 10 lines of case space, right? 10 views per segment is the term that we typically use in that situation. If I take 10 views per segment, then essentially I now have only 10 heartbeats I need to get the same 100 phase encoding steps. I've now reduced my time of acquisition to half of 20, which is 10 seconds, quite doable. But think of what's happening to the temporal resolution at the same time. I've gone from 5 lines to 10 lines. So my temporal resolution has become worse as I use more views per segment. Let me put that to you in another image. This is just an example of how that might occur. So if I need more views per segment, then basically I can acquire it faster with lower number of heartbeats, but I have now lowered my temporal resolution. If I use if I want a higher temporal resolution, let's say I'm trying to evaluate valves, or I really want to see the endocardial border better in that patient, then I need to reduce the number of views per segment to be able to get a higher temporal resolution. You can also use something called view sharing, which is similar in concept to the keyhole method that I showed you earlier, where you can share parts of case space between different adjacent frames and hope to get good quality images at a faster rate. Okay. This is what you might see on your screen. And I'm going to show you this as well. So here on my Siemens screen, I'm seeing the number of segments here as 16. Okay. PR tells me the temporal resolution of this particular exam. and TA, the acquisition time, tells me that for a single image, for a single breath hold image, I take 6.7 seconds. Okay, 6.7 seconds with a temporal resolution of about 44. TR here is not repetition time. Please remember that, right? Because I'm taking multiple lines together. So TR here is not repetition time. It indicates temporal resolution. Now, this is 6.7 seconds. This graph here, this little table here will tell you what happens when I change the number of views per segment. As I increase the number of views per segment to 28, from 16 to 28, my temporal resolution worsens from 44 milliseconds to 77 milliseconds, more blur artifact, for example. But my time of acquisition is now 3.9 seconds. If this person was able to comfortably hold his breath for longer periods of time, I would definitely choose to reduce the number of views per segment, go down to 12, improve my temporal resolution of about 33 milliseconds, and be able to get a reasonable acquisition of about 8 to 9 seconds. To put this into perspective, when you're doing an echocardiographic image, the temporal resolution of echo is in the order of about 5 milliseconds. When you're doing a CT scan, the temporal resolution is on the order of about 100 to 150 milliseconds. So for an MRI, we really want to be closer to the echocardiographic range. So our preferred temporal resolution is between 35 to 45 milliseconds. It's really where we want to be at to be able to get good quality images. So this is again just showing you the same thing, where by reducing, and here are my options here, I can go from 2 to 61 by reducing the number of segments that the views per segment. I have changed my temporal resolution to 5.46 compared to 35 milliseconds. So you can see that there's a significant change in temporal resolution, but at the cost of the time of the acquisition. Okay. The calculated phases is simply the magnet saying, okay, you can acquire 10 phases, you can acquire 15 phases in your RR interval. If you want to see 25 phases, I will interpolate the information and give you 25 images for that particular examination. This is to put it into perspective. On the image on the right, I have deliberately taken a very large number of segments. What does that do? It basically reduces my breath hold time to 1.3 seconds, but worsens the temporal resolution. So if you look at this particular image, you can see that the endocardial border is somewhat hazy and ill-defined. You can see the mitral valve is clearly also ill-defined on this particular image. If, on the other hand, I had a much better temporal resolution of 16, with a smaller number of segments of 16, my breath hold has increased from 1.3 seconds to 8 seconds. But I want you to appreciate the fact that you are now able to much more sharply identify the endocardial border and also the valve planes. I think this becomes self-evident that the way you fill up K-space is critical in terms of how you control temporal resolution as well. The second unique feature of K-space is the concept of the greatest separation between the line or undersampling results in a phase wrap artifact. And we can then use that phase wrap artifact in the concept of parallel imaging. So here is the example that I showed you earlier, right? So this is the standard K-space filling, which gave you a full field of view. You can see here when you undersample K-space, the dots that you're seeing on this image on the left, on the lower image, are clearly spread out much further than this finer dots that you're seeing up here in the upper left-hand corner. But what you see occurring from this spreading out or undersampling is a smaller field of view. So Rajesh, maybe I can take a small break here and see whether there are any questions from you or from the audience, and then move on to the second part, which is about parallel imaging.
Yes, thank you, Sanjaya. Yes, we'll continue after a short break of discussion. I request everyone to send their queries in the chat box so that these queries can get answered. So Dr. Sanjaya is discussing very important points, and mostly is discussing the all practical aspects only. It is impossible to understand completely about the exact physics what is happening there, because it involves not only physics, it also involves the mathematics. under the probabilities which is beyond the scope of understanding. But whatever points he is discussing, like the understanding that the center of the case space is very important for the image contrast, whereas the periphery of the case space is important for the image definition, the so called the spatial resolution will be better in the peripheral line of the case space. So one of the practical aspect where we can use it is in MR angiography, like he rightly pointed out, because some of these options are is given by the in some of the vendors are giving the options to the at the time of the scanning. These are the options available. We can choose whether you want a elliptic centric case space filling, where when the contrast density is maximum, the center of the case space will be filled, which is more important when you are doing the MR angiography. So you can manually select these options are possible. So if you know that when to select it, you can use this. So depending on the arrival of the contrast timing, so we can use these options. And the other important thing which is rightly pointed out regarding the temporal resolution versus the number of segments which we are acquiring per the heartbeat. So as we increasing the number of segments, your scan time will be reduced, but the temporal resolution will be bad. So as a rule of thumb, I used to do in such a way that it's very difficult to remember the exact numbers of the temporal resolution and adjusting it. But if we can keep adjusting the number of segments with the scan time of at least 10 to 12 seconds, because most of the persons can hold their breath for about 10 to 12 seconds. So if you can keep it like such a way that each image is acquired within 10 to 12 seconds, then you always get a more or less consistent temporal resolution. So that is one way of doing it. And there are few queries, Dr. Sanjay, what will be the typical TR should be for valve evaluation as compared to the routine scan? Do you recommend any specific temporal resolution?
So the temporal resolution is very simple to understand. On a Siemens magnet, at least as I showed you on the screen, the TR it tells you what the temporal resolution is.
Yes.
And if you're in the close to the 40 millisecond temporal resolution, you will get very good quality images.
Yes.
35 to 45, and you can change it based, as Rajesh said, on the patient's ability to hold his breath. If the patient can hold his breath for a slightly longer period of time, you can alter that to improve your temporal resolution and maintain it around 35 milliseconds.
Yes, yeah, around 40 seconds, 40 milliseconds. I mean, not seconds, 40 milliseconds is the ideal. Yes, yeah. So, and someone is asking, can you repeat about the types of filling? Maybe the centric, case space versus.
If you look at this particular image, what you see is essentially the whole concept of case space is very simple. You need to fill up the entire case space one way or the other in order for you to get an image. And you can start to fill it up from the bottom to the top, like I showed you that pulse sequence diagram with those arrows pointing to different lines in that simple 8x8 matrix. You can start to fill it up from sequentially from the bottom to the top of the case, to the top. In which case you go through the center of case space somewhere in the middle of the acquisition. Alternatively, you can choose to fill up the center first and then get the edges after that. Third way of doing it is by using a spiral technique or a radial technique, which is a little bit more complex in terms of how it basically uses the case space filling. So the center is called centric. If you go from top to bottom or bottom to top, it's called sequential. If you share the central information, if you share the peripheral information over a series of images, then we call it keyhole, or keyhole was actually a GE term which was initially used, but those are shared views of using the peripheral information over multiple different image acquisitions. What's important for you to remember always is that you don't really control where you want to fill it up and so on and so forth, but you can control how the type of filling that you use. Simple example is when you do a runoff in the abdomen and pelvis. So when you're doing a runoff, your triggering typically occurs as the contrast reaches the aorta. So the contrast is very high in the first set of images that you get in the abdomen. Hence, a centric type of filling for the abdominal phase of the MR angiography is going to be very good. As you go more distally, there is more dilution and takes a longer period of time in the thighs and in the calf regions. So you switch from a centric filling in the abdomen to a sequential filling in the pelvis and in the thighs and in the lower extremities. Now, when I say you switch, it's not that you are actually going to the MR magnet and changing these things on your own. These things are automatically built in as the best pulse sequences by the manufacturer. When you do this, you need to understand when that occurs. Now, if by some chance you're doing a centric filling, but you start before the contrast comes into the aorta, then what might happen is that the center of K space, when you get in that abdomen, and I hope you can just imagine this happening, you're getting K space, but when the contrast comes in, you've already filled up the center of K space and you're getting only the edges then. So then what happens is you get a very odd looking image because the center is completely dark, the lumen is dark, and the edges are super bright, right? Because you get edge resolution because you started it too early in that situation. Does that make sense? So that is the reason why the timing of the bolus is very important, particularly for MR angiography that you use. Simply put, to answer your question, sequential is going from one end to the other. Centric is when you fill up the center first, and then you go on either side and you fill up the periphery of K space. Rajesh, any other questions?
Yes, there somebody is asking, can you explain the relationship of the number of segments taken with the time of acquisition? Yeah, that's what he has already discussed. Is higher the number of segments, the scan time will be less. Lower the number of segments what you are using, the scan time will be higher with the better temporal resolution.
So again, think of that as a very simple manner, in a very simple manner. Okay, same story. You need to fill up your K space to get an image. Let us say the K space for a particular cardiac image needs 128 phase encoding steps, 128 phase encoding steps. You can fill up the 128 phase encoding steps as two big blocks of 64, right? Two simple big blocks of 64 can be used for that particular thing. Now, those are two segments. You can alternatively use 16 big blocks. So you're dividing that 128 into 16 different blocks, 16 heartbeats. You can divide it into 40 segments, okay? So segmentation is nothing but dividing the total number that you require into individual blocks. Now, what you have to understand is the views per segment that you get is a little bit different, right? So that's the concept of segmentation. Segmentation is how many blocks do I need to basically get my entire image. Now, in my views per segment in the first example, when I take just two segments, my views per segment is 64 because I need 64 lines, 64 views to be filled up, right? So that box that I'm showing you here, that box which I showed you earlier, that box, the number there is the number of views per segment, 64. Very fast imaging, just two heartbeats, very low temporal resolution. If I change that views 64 into say 32, then the same 128, I've gotten it in 4 heartbeats, but I've reduced the number of views into 4 different groups. Do you understand that concept? So there is a difference between the views per segment that you use representing the number of lines of K space that are filled. This is going to be discussed, I'm sure, in the subsequent lectures once again when we're talking about cardiac acquisition techniques.
Yes, I think we can move on to we will continue with the lecture. Yes.
All right. So essentially what I mentioned to you here is that here is the K space. Normal spread of K space gives you a full field of view. Undersampling of K space gives you a smaller field of view. All of you are very familiar with this phase wrap that you've seen in multiple standard images where you undersample the phase encoding axis and you end up with areas of the anatomy overlapping with each other as well. So that's a simple example of the practical example of undersampling of K space. Now, if you have specific coils, and remember we use anterior and posterior coils, right? So if you have specific coils and each coil has its own receiver, in other words, each coil is able to get its own individual information back from that particular image, then what we can achieve is something called a coil map. So what you're seeing here on the left part of the images is the coil map. And on the right image, you're seeing how the coil map corresponds to the image map that you're seeing there as well. So potentially, each of these coils can then be combined to give you a full set of information. And you can get this only when you use specific coils or specialized coils, which have its own inbuilt receiver or is able to look at its own local sensitivity, right? Local sensitivity is what I'm showing you here. This is then converted into a concept of parallel imaging. So let's go back and look at this particular image that I'm showing you here. On the left-hand side here of the line is the entire case space that you need to acquire. I have now reduced the number of lines by 2. I have undersampled it by 2. What that simply means is I have deliberately given a phase wrap, and I have caused this phase wrap to give me an aliasing. But because I know the sensitivity map of both the coil, I know how much of aliasing that I am giving into this particular image. And I can now correct for the aliasing and give you a fully reconstructed image, even though I have undersampled the case space by 2. How does it improve my time of acquisition? Remember, number of lines of case space, the number of phase encoding steps multiplied by the TR is the total time of the sequence. So I have now reduced my time by approximately 2. So if this was a 10-second acquisition or a 20-second acquisition, this has now become a half of that. Right? So this is an example of parallel. So essentially, this is exactly how the images are seen. Each of these will give you this degree of wrap. There is a coil calibration sequence which is done prior to doing this, or usually prior to doing this. Some vendors might do it prior for the entire sequences. Some might do it beginning of every single sequence. This coil calibration is now used to unwrap these images and give you a full example. And we call this sensitivity encoding because it relies on the sensitivity of the coils. An alternative way of doing parallel imaging is imaging in case space. Again, the same example, you want to get all of these lines. You have undersampled by 2. But in this situation, the coil calibration is done even before image acquisition. And the coil calibration here basically is done not to unwrap the image, it is to fill in these lines of case space which have been missed out when we've taken this. And notice that this is just a simplistic way of showing it to you. The red dots are the ones which were acquired. And the red, you can interpolate the information that you get from the red dots to fill up the middle absent line, the green dots, right? So this is an example of how parallel imaging occurs using the case space option of SMASH or GRAPPA, as I showed you in that. Same, you get the full degrees of case space, and then you get it into an image here. So essentially, you have sensitivity encoding, which is an image domain technique, as I showed you. You have SMASH and GRAPPA, which are case-based domain techniques, which use individual understanding of sensitivities, both of which use sensitivities to basically get your images. Because it's using the sensitivity profile, and because you are getting a certain degree of phase wrap, you can get artifacts such as this, where you can see here, this artifact is basically the upper abdominal wall that you're seeing, the abdominal wall artifact. This might be the posterior abdominal wall artifact that you're getting superimposed on each other. And here this is, you can see that the top image has a higher R factor, the lower images have lower R factors, and therefore the wrap is less on the lower images as compared to the upper images. How does this convert in terms of our usage of parallel imaging? This is a little bit of a blurry slide, but we had to take it from a screenshot. And you can see here that we're using the PAT mode GRAPPA, which is the case-based domain parallel imaging technique. We're using an acceleration factor of 2. And we have a signal to noise ratio of 0.96. If you use a factor of 3 instead of 2, notice that the signal to noise has decreased, is now 0.78. So the important point here for you to understand is we have increased the speed of the acquisition, but we have lowered our signal to noise ratio and with the potential of getting new artifacts in that particular image as well. By increasing the speed of acquisition, notice that the acquisition time has gone from 6.5 seconds to 4.5 seconds. Notice that the reference scan is integrated within this particular imaging time as well. Okay, so do all of you understand this? Using higher acceleration factors often results in decreased signal to noise with the advantage of improving speeds. So this is an example taken from the literature of what an R4 or four speed parallel imaging might look like compared to the R2. Notice the extensive noise that you're seeing here on the image on the right. And typically the amount of noise that you're seeing here on the R4 is at least double that of the noise you're seeing here when you just use a IPAT factor of 2. So this is an example in real time when you can use grappa in a free breathing patient where you can see that the patient is not able to hold his breath, but you're trying to get relatively good images that you're seeing here. Similarly, again, the patient is not able to hold his breath for the delayed enhancement images, and you can get your single shot imaging to look for the areas of delayed enhancement in the inferior wall of the myocardium in this patient with myocardial infarcts. But notice that you, in both of these instances, you have increased amount of noise in that image. This is a little bit more of a noisy image. What do we have coming up in the new horizon of parallel imaging? There are certain terms and certain things that you might hear from your vendors and certain terms that you need to be familiar with. These are complex terms. And basically one example is that you can improve the ability to get acceleration by using parallel imaging results with higher acceleration. This is just one example of how that's being done. So to show you the image on the left, the red lines are the ones which are acquired. This is a 3D sequence. So the x-axis is actually deep, and the partition gradient and the phase encoding gradient are shown in this black square. So what you're seeing here are these two lines have been acquired, and you've missed out 3 different lines. And you know that you're going to get some artifacts from the absence of this information. So how do you fill up some degree of information within these 3 lines? You can do a second, instead of doing a 4 acceleration factor here, it's called 4 acceleration, by the way, because you get 1 line and you skip 3. So 1 out of 4, which is why you have an acceleration of 4. But you could potentially get the same 4 by using an acceleration factor both in the phase encoding and in the partition gradient as well. And then you get a sort of a more symmetric distribution. You can then even use a phase shift that is occurring here, where you take these dots and you interpolate them into areas which are completely lost. And this gives you an even better image that you see here. This is an example of using the above technique to speed up acquisition in the liver, again taken from the literature. And what you see here is at 0 seconds, 2 seconds, 4 seconds, 6 seconds. So you were able to basically get almost 72 slices at 3 millimeter thick slices using a acceleration of factor 4 using the previously mentioned technique, and still get very good quality images with dynamic phase information every 2 seconds. Even more complex is something called KT blast. I'm not going to try to explain it to you, but I'm just going to give you the information that this has. Essentially, K we already know is K space, and we know that the K space where's a parallel imaging I've just gone over with you. T stands for time. So potentially what they're talking about here is that you not only can do acceleration in the K space, but you can also do it in the temporal domain as well, in the time domain. And you get something which is very complicated, such as this, using various different filters to basically get reconstructed images using both K space and temporal domain undersampling. Perhaps the newest kid on the block is something called compressed sense imaging. And this is actually fairly intuitive to something that we are already familiar with. We all use lossy compression frequently, right? You take images on your screen, you want to share it with somebody else with WhatsApp and so on and so forth. And you're sharing these images, and the images look very good as they come across. but every one of these have got certain losses in the amount of information that's actually there on the screen. Some of you may be using PACS, where the PACS vendor has deliberately reduced the information that is being transferred across the internet so that you can see the images faster in real time as well. So we are already using this lossy compression. And the concept of using this wavelet transformations, checking a acquired image and the proposed image and comparing the iterative nature of the actual image to the expected image, checking for data consistency, repeating this process till you get as close to data consistency as possible is something that's called compressed sense. And I'm sure that you'll hear more about this in the future as well. All of these require large amount of computer intensive information. So the last kid on the block is basically this artificial intelligence, which is taking input images, even from compressed sensing, going through different types of architectures, artificial intelligence architecture, to be able to give you output images as well. This is a good article that I would refer to all of you to review all the different types of rapid cardiac cine MRI. Curtis and Cheng, it's in 2022. It's among the most recent articles that you'll come across. Journal of Magnetic Resonance and Imaging. So in summary, I hope I've given you an understanding of K-space. Understanding is critical to get good images and understand artifacts. I've also explained to you that you also need influence of speed of acquisition. Parallel imaging improves speed. And we are now fast approaching faster imaging techniques. And I think you heard Lata Mangeshkar say it perfectly in her song right now, that Dil Dhadakna Hai, and we are trying to get excited by this and also excited by what we are learning about K-space. Thank you again for your attention.
Yeah, thank you, Dr. Sanjay. Very nicely explained all the important facts. There are what does acceleration factor mean? Yeah, that's what is explained. The factor whether 2, 4. Yes.
So acceleration factor. Remember, so you need to fill up K-space one way or the other. So if you need 128 lines of K-space and you've acquired only 64, your acceleration factor is 2, right? Because TR multiplied by the number of phase encoding steps when you use 64 is half the time taken as that of a TR multiplied by the full 128 steps. So therefore, a acceleration factor simply implies how fast you're able to fill up that K-space compared to the original image. Technically, it basically implies that you're taking every alternate line of K-space. If you do acceleration factor of 3, it implies you're taking every 1 in 3 lines of K-space is being filled. The acceleration factor, your time to TR multiplied by that is 1/3 that of the original image, is 3 times faster, and so on and so forth.
Yes, Sanjay, I have a query. What about the size of the K-space? Will it be affected by the different field of view, say a 20 centimeter field of view versus 40 centimeter field of view, or will it get affected by the say the matrix size, 256 versus 512 into 512? So whether will that affect the size of the K-space?
So the size of K-space is a frequency space. So the size of the K-space, that's a good question. It is controlled by your number of frequency lines and your phase lines. So the size of the image itself will not be changed. It is really the number of frequencies that you use in the frequency encodes, the number of phase encodes that affect the size of K-space.
Yes. So in other words, most commonly what we are using is say 256 into 192 matrix. So it will have a 256 data points along the x-axis and the 192 lines of the K-space lining in the y-axis. Yes, so I think some of the important points what you covered is include the one is the auto calibration. I mean the calibration scan what you talked about. Actually, many of the technicians actually don't understand that calibration scan what was being done. In some of the vendors like a GE, they allow to do this calibration scan before doing the actual scan, and even the images also will come separately, and people don't know what the importance of that. So those things have the very important information about the coil position and the different elements sensitivity map are included in that calibration scan. So it's very important to do the calibration scan correctly, and especially if you are doing a chest or the abdomen scans, we have to do the calibration scan also with the breath hold, so that the exact coil element will be known to the system. So that point is very important, and like you rightly pointed out, that calibration scan either can be done before the scan, or some of the sequences like grappa, it is an auto calibrated scans. So where the scan time will be slightly longer, because it's doing the calibration at the time of the scanning itself, as compared to the sense where usually the calibration scan done first, then only the actual scanning will be going on.
I have another question here which says that what sequences in cardiac imaging will you recommend faster methods like GRAPPA 2 or 3, and where would you not recommend it? So the answer really is that every time you use a faster acquisition method such as parallel imaging, you have a lower signal to noise. So you want to use it in areas where you need that faster scan, you need that increased time of acquisition, but you don't necessarily need that worsening of that. You don't worry too much about the signal to noise. So for example, if a person is not able to hold his breath and you really want to get a better image, then you can do it. But if the person is able to hold his breath, then typically I'm still old school in that I prefer to use a acceleration factor of 2, because with an acceleration of factor of 2 you still get very good quality images. But as you go to larger acceleration factors, you get poorer and poorer signal to noise when you go to that. And as Rajesh also mentioned, that it's not exactly double or triple benefit that you get, because the calibration scan is also included in that particular time that you're using. So mostly cine sequences is where you tend to use faster parallel imaging, but certainly you can use it for static images as well if the person can't hold his breath.
Yes, that newer concept like compressed sense also is important, because many people know that when you say parallel imaging, they know is this iPad, and compressed sense, we should not think that is just an extension of that iPad. It's a completely different method by which it is done. So only thing is, it's a newer methods, and if you can get that option, it is always better. Someone asked for a reference. I have posted it in the chat group. And these records as well as the previous versions of the lectures will be available at our IACA website. So please visit our IACA website. And with that, we will come to the end of the session. I once again thanks Dr. Sanjaya as well as Dr. Richa for arranging all those things. So we'll meet next month. Dr. Pudivan, anything else you want to add?
Yes, I just want to thank Dr. Sanjaya sir. That was an excellent presentation, and it was a very difficult topic, at least for me. I struggled a lot with understanding K-space during my initial days. So it was an excellent talk, really. And I also thank Rajesh Kannan sir for excellently moderating the session, and giving his inputs. As sir told, this particular session, as well as the previous sessions, the recordings are available at the ISE website. So these are the case space and all. These are a little difficult topics, and it's not like you can't understand them. You just need to repeat it multiple times to get a grasp of what it is actually about. So the recordings will be available. You can just see it again and again. And when you see multiple times, and every second time you see it, you tend to understand a different concept in the explanation. And you can just keep on seeing it n number of times, and you will still be able to understand one different concept that you didn't understand before. So that's a good thing that these are all recorded. And so the next session of the series will be on April 6th. So that session will be more focused on cardiac imaging. So the sequences that are used in cardiac MR, the basic sequences that are used in cardiac MR, and the physics that are more oriented towards these basic sequences that are exclusive for cardiac MR. So we will be seeing about that in our next session. And again, I once again thank Sanjay sir and Rajesh Kannan sir for this wonderful session, and thank you all for attending this.
Thank you.
Yeah, thank you once again.
Thank you, sir.